Okay, so I'm going to real quick talk about the DNA replication. So some of you may not be understanding very well. So DNA replication, we want to make sure something you understand. Number one, this is a semi-conservative. Conservative, okay, which means the daughter cell and the mother cell, they should be exactly the same, but they may have some difference because of the mutation happen. Second, this is always from 5' to 3' in the direction, and the enzyme is called DNA polymerase. Now we will talk about there's different type of the DNA polymerase. And the gene base corresponding rule is always A complement with T, G complement with C. They are connected with hydrogen bonds. And GC, you see there is a 3 hydrogen bonds, so usually it's much stronger than AT. So when you do the PCR, the design primer, you need to think about the GC components and amount. Okay, so we much more important is going to talk about all those enzymes, the function during the DNA replication. So here what I'm going to draw is to help you to understand. First of all, there is 2 bonds going around in anti-parallel and a different direction. This is 3' to 5'. The second one is 5' to 3'. Now, at the beginning, this is double helix. So everything happens, which is at this replication fork. Now, at the beginning, they want to start a replication. They need a group called a DNA group, Dna group, which is encoding A, B, C. Now, Dna A, this is initiator, which means they start to do the replication. Dna B is a helix. What's the function of helix? Which is unwind. So your double helix, which is twisted, I want to take it out. So all untwisted. Then the C, this is a helper, which means it host of DNA B. So those are called initial protein, or we say it's an initiator. So that's a DNA group. Then, once these 2 bands has been separated, because it's always twisted, anti-parallel, so we need to make sure they are all separated. That's why we need some of the protein to make sure they stay separated. They will stay separated. These are called SSB. That is single strand binding protein. Okay? Now, we're going to talk about the replication. You have 3' to 5' and the 5' to 3', 2 bands. The first band, we call it leading band. Because they can do a replication naturally, and the direction is always from 3' to 5'. Now, what that really means, lots of people don't understand it very well. What that really means, which means the direction 5' to 3', which means you read mother bands from 3' to 5', and synthesis, new bands from 5' to 3'. Now this rely on DNA polymerase 3. Okay, now you learn in your other classes. This is called leading band. Now the other band, there is a problem. This is called a lagging band. Lagging band, you cannot do the replication naturally. You need some help. What's the help? So this is 5' to 3'. We cannot do it. We can only do is 3' to 5'. So these type of stuff, you need those small segments. And those small segments, you also need some of the help. These help, which is an RNA primer. And this RNA primer is composed by polymerase. Now, the question is, why this lagging band, you cannot do it naturally? The reason is there is no 3' free hydroxy bonds. Okay, so every time when they do, you must have this 3' free hydroxy bonds. If you do not have this hydroxy base, you cannot do the replication naturally. But for RNA, there is no problem for that. They do not have this restriction. So therefore, they have these RNA primer to start it. And then they go through this direction. They start to have those small segments. Now, what's the name for those small segments? Called Okazaki segment. This is by a Japanese scientist. Okay, so these small segments, Okazaki segments, has been generated. Okay, one by one, one by one, one by one. Okay, we have to cut these RNA primer. We don't need these anymore. So what's the function to cut those? So cut primer. This is by DNA polymerase 1. Okay, now all these things are cut, and then we need to make sure they have been connected. So what we need? Then we need something to help them connected. This is called DNA ligase to connect it. Okay? So then they can be finished, all these replication for the lagging band. Okay, so then there's something else. This, DNA is anti-parallel and double helix. Okay, at the beginning, this is always negative supercoiled. Now, once you do the replication, they separate it. It will become a positive supercoil. That's not good. We don't want that. So there is something can fix it. They want to make sure this positive supercoil is not happen and then become negative supercoil. They need an enzyme. That enzyme called topoisomerase. Topoisomerase. Topoisomerase, what that means, do you know topoisomer? That is a branch, this simply of geometry. So talk about the geometry of the space. So that's where it comes from. So topoisomerase, which is a function which changes the space structure, you can say, the cubic structure of that DNA. That's why it changed from supercoiled, positive supercoiled to negative supercoiled. Now the topoisomerase, typically in E. coli, it's called DNA gyrase. Okay? Then something very important. During this replication, there is a mistake happen. Then the mistake happens all the time. Therefore, we need somebody to do proofreading to solve the problem. It's like you write a manuscript. You have to do a proofreading of the grammar. Is there any mistake? No, there's lots of proofreading system. If they didn't do a good job of proofreading, they may generate a mutation. So when they do the proofreading, the first thing what they do is called the scanning, just like a very easy scanning to see is there any mispair. Okay? So what's the function for this one? Which enzyme to use this one is the proofreading is conducted by DNA polymerase 3. Okay, now we go back talk about the DNA polymerase. DNA polymerase, we have 1, 2, 3, 4, and 5. We don't mention DNA polymerase 2. I don't know about that. DNA polymerase 1, this is to remove RNA primer, which is small segment in Okazaki segment. Okazaki segment. This one we don't know. This is polymerization and proofreading for DNA polymerase 3. How about the 4 and the 5? This is for SOS recovery. We're not going to mention this semester. For most of the time, during their replication, there's lots of mistakes going to happen. We mentioned them. The DNA polymerase 3 only is scanning to see the mispair. Okay, then they can nick it out and put a corrected gene base there. But lots of the time, it's much worse than that. In a life-threatening situation for bacteria, they need something to recover. They have to start an SOS recovery. And the DNA polymerase 4 and 5 is play an important role in that part. Okay? So these are what I'm talking about. I gave you an introduction. Talk about DNA replication. Besides all these talk Dr. Peterson gave in the slides, so I just give you some easy language to understand it, because you may not learn the genetics yet, so I just gave you draw on the blackboard to let you understand. Okay? Thank you.